Hello and welcome everyone, and thank you for joining us today. This is the fourth webinar in the Conversations with Colleagues series, which is being hosted by the Transportation or the TRB Bicycle and Pedestrian Data Subcommittee. These webinars take place every fourth Tuesday of every month, or every other month, excuse me, and are focused around challenges in bicycle and pedestrian traffic monitoring. Today's session will focus on various methods for collecting bicycle and pedestrian data using video. My name is Nathan Hicks, and I'm a transportation planner at CDM Smith in their Miami office, and I'll be moderating today's session. We have two panelists today, Bernardo P.S., who is a project scientist from the Robotics Institute at Carnegie Mellon University, and also Dr. Tariq Saeed, who is the director at the UBC Bureau of Intelligent Transportation Systems and Freight Security. Just as in the previous conversation webinars, the aim for this series is to allow for a more conversational tone. The hope is that as the discussion progresses, questions can be raised not only to the speakers, but to one another. If you have a question, you can either type it into the question pod or you can raise your hand on the interface on the right, and we will unmute your microphone so that you can go ahead and speak. We'll go ahead and test that raise your hand feature now by having everybody go and doing that to ensure that it's working. All right, I see a bunch of hands going up. Great. All right, thank you, everybody. Greg Lindsay from the University of Minnesota will be monitoring the question box as they come in for the Q&A sessions. If you are having audio issues or any other technical problems, please be sure to type into the chat pod or the question pod, and Miley from TRB will be assisting with any possible technical issues that we have. Thank you, Greg and Mai. Following the webinar, we'll be providing a summary, which will include any links or references that are made throughout the webinar, as well as a recording. Our goal for today's session is to introduce methods involved and issues involved with collecting bicycle and pedestrian data with video, to provide an overview of an effort underway at a university, and to build a community of practitioners and researchers who are advancing the non-motorized traffic monitoring field. And with that, we will move over to our first panelist today, Bernardo Pires. We will give you the screen here, Bernardo, so you can go ahead and lead us through your session.
Okay, hello everyone. Like Nathan said, thank you for the introduction, Nathan. Thank you for the invitation, for having me. So I'm just going to have to run through a few slides that I have. I don't want to go too long. This is a very high-level overview of some of the projects that we're doing here at Carnegie Mellon, and then obviously we'll have enough time for questions. So I'll welcome any questions that you may have. I also put my email here in the slides. I believe that the attendees will have access to the slides. So if any questions come up, feel free to email. Also, if we don't have the time for that today. I just wanted to point out, obviously, as most university efforts, this is a work from multiple people. I'm the principal investigator for this project, but I've been very happy to have the help of Mehmet Kokamas, Chris Kafin, John Kozart, and Jung Gong that have been working on this for the last about year and a half. This project, I also wanted to mention that this project has received support from the University Transportation Center here at CMU. As some of you may know, the University Transportation Centers are actually supported by the DOT, our federal national DOT. And we actually had support from two different ones during the years. Technologies for Safe and Efficient Transportation was a transportation center that's just winding down now here at CMU, and in its place we're kicking off Mobility 21. I point them, for those interested, I can point them to the website. There's a number of projects in the transportation and that they've supported. It may be of interest to some of the attendees. Anyway, moving on, this is the project that we've been developing here at CMU. Is similar to some of the things out there, but we're taking one of the main focuses has been from the beginning on the pedestrian and bike aspects of transportation. So we've had two versions. I'm showing here the first version of our data collection, pretty big just to test out some of the methods. We had pretty much a camera mounted on the top of a collapsible pole. This is similar to the device that you might have seen from MyoVision. The objective here was for us to control the hardware, control the quality of the images, get some images that were possibly a little bit higher quality than what you get from MyoVision. And our first step was just to collect some data near CMU. The focus of the initial project was actually to work for the city of Pittsburgh, specifically targeting the bike lanes here in Pittsburgh that were installed in a somewhat contentious project. And we wanted to see, try and measure the usage throughout the year. There was the question of Pittsburgh with some winters that can be significantly cold. There was a question of how much usage the bike lanes got. And so we tried to target that. As a first pass on how this was done, we collected 10 hours, we collected 50 hours of the video data, and we manually labeled about 10 hours of data. So this was a large effort to label and to collect data. In those 10 hours, we labeled essentially about 1 million frames, seen 500 pedestrians and about 100 cyclists, 111 cyclists. So this is a very, very high level overview. I don't want to go into many details, but essentially we're trying to build an algorithm here that will allow us to count pedestrians and bikes. So at a high level, there's three steps, three stages here shown on the left. There's a detection stage, a tracking stage, and a counting stage. During detection, we have basically a two-step detection. So the first step, we just try to find people, be they either bikes or pedestrians. And on the second step, we're trying to distinguish between cycles and pedestrians. Then once you have those detections, so basically these detections occur on each single frame of the video, then the question is to track them so that we can figure out the path that the bikes or the pedestrians are taking. The tracking is achieved by basically multi-clue clustering. So essentially we're trying to cluster all the detections into paths that the pedestrians or the bikes are taking. Those paths are found by using multiple cues in the environment. So there's a foreground detection, a geometry prior, and a movement prior. So this is just a very high level to give a sense to the attendees of what's going on. Once you have the clusters done, you basically have tracks. So as you can see in this image on the bottom left, you have tracks of what the pedestrians are doing, where they're coming from and where they're going, and the same thing for the bikes. In this particular image that I have here, we just placed this red line here in the middle, and we were doing the counts as pedestrians or cyclists crossed that line, and that's how the counts were done. So actually, I believe I have a video here just to illustrate how this works. So you can see a bike, two pedestrians going from bottom to top, and one pedestrian from top to bottom. The bike, I'm not sure if this is visible. I hope it's visible. It's for the attendees online, but there's some lines, for example, some green tracker line that's going up here from top to bottom. And you can see that as, I'm going to rewind, as the pedestrians or the cyclists cross the line, that they get counted and the counters get incremented. One thing that some of the attendees may notice is that the lines actually fade away once the people are too far to the top or to the bottom of the image. This is mostly actually done on purpose because we really only care about the region around the line that's doing the counts. I don't think there's anything else. Just playing it again one more time. And so in a large data set, you can imagine we have a significant number of hours that are taken. Right now, for example, we have hours that have been collected in multiple suburbs of here of Pittsburgh that we're trying to count. We also receive data from the Virginia DOT. And so in a large data set, one of the challenges can be that processing all that data. As you can imagine, since you have to basically go through all the frames in the video and then track the pedestrians from frame to frame. Next slide. This is just a very brief overview. It's actually published. Since this publication, we actually improved our results, but we published this during 2017. The results in our original data set. I have what's called a confusion matrix. So the confusion matrix just shows that if for each pedestrian or bike scene that was truly there, how many times was it actually counted, predicted, basically by the algorithm, and how many times it was missed. So as an example, in the true case of pedestrians being seen and pedestrians being predicted, this is a correct prediction. We have 9,568 predictions. There was 4 times when there was a bike there, but we thought that we'd seen a pedestrian. And for example, there was 11 times where there was a pedestrian there and we thought that we'd seen a bike. So with any methods, I think this is also something to point out for the attendees. No method is completely 100% accurate. Our method showed 95% accuracy. I also have some example of the errors that this type of methods can make. And these are nice not only to show what happens. For example, this pedestrian here was not seen, was classified as a background. This pedestrian here was also classified as a background. In these two examples on the left are good examples of what can happen if the pedestrian is too far away, then it's too small to be seen. Or in the case on the second image, it was actually a problem of the vegetation, sometimes occluding or introducing some movements, and there wasn't a clear view of the pedestrian for a good amount of time. The other 2 examples on the right show a pedestrian that's been classified as a bike. You can almost see as a human that this is also a case where a person might be confused, at least with a single frame, because there's a little bit of a shadow, and it had rain, so there was some water on the ground that created some patterns, made it harder for our classifiers to actually pick out if this was a bike here that the person was standing on, or if it was just a person walking. And this was the reverse. There was a bike, but it wasn't really visible on the image itself. And so with this, I believe this is my last slide. Yes, I just wanted to give you a brief overview of our methods. One other thing that I wanted to sorry, I have one more slide. Yes, here we go. So one other thing is just to give an update. The images I've shown you before were from a publication that we published last year. Since then, we've been taking more and more. We've tried to open up a little bit for the industry, and we've volunteered to do counts for non-profit organizations, oftentimes bikes and pedestrian advocates, and we also for governmental agencies. We actually set up a website to receive video that partners may have collected that they may want to count. And so one of the things that we quickly realized when working out of the academic and trying to serve the public, or trying to serve engineering firms or the federal government or government agencies, was that oftentimes significant decisions are going to be made. And I guess for all the traffic engineers listening to this is pretty obvious to them. Sometimes it's not as obvious for the academics. So when you're going to make significant decisions, you want to make sure that your counts are accurate. So one of the things that we as academics had to change a little bit was to not just trust our algorithms blindly, but we have been actually placing a human in the loop. And I think that's one of the challenges, is to progress since we don't have 100% accuracy guaranteed. How can we have a human in the loop that's helping the computer, but it's not necessarily brought down to the level where it has to check every single frame? because checking every single frame, that's just counting manually. That's not what we want. So right now, our current algorithms that are being developed here at CMU actually have two things. One is that they are able to quickly fast forward through the video and have a human look at the annotations that are being produced by the machine and to verify those annotations. And also number two, we have the option to flag the cases where the annotations are not as confident. And so kind of find situations where the confidence level is relatively low and then prioritizes those to be shown to the human. So the idea is to reduce the workload while maintaining assurances on the quality. We've been trying to open the access of this since it's been a university project, but we've been trying to open the access to non-local entities here in Pittsburgh, not just Pittsburgh, but also away from Pittsburgh, and we've incorporated the human loop to guarantee performance. So I invite pretty much anyone that's out in the audience and that has that's going to produce counts and that is working with either a government entity or a nonprofit organization that supports bikes and pedestrians counting to reach out to me if they have a data set that they want us to analyze. We can definitely offer that. And right now we actually have the funding, so we don't really need any type of payment from the attendees. So that's really pretty much all I wanted to discuss, Nathan. I don't know if there's already any questions out there, or if you want to wait for later on for questions.
No, we'll go ahead and move into ask the Q&A section for you.
There's a question now. And the question is, how can we send video to Bernardo? And what's the website where we can upload it?
Perfect. So the best way is actually, we don't want to open up for everyone. Like I said, we have funding to help, but not unlimited. So we are not ready to open it up for everyone. What I'd invite any of the attendees is to just email me directly, ppyrus@cmu.edu. That website is actually available. There's a link from, I can actually add it at the end when we give the extra materials to the attendees, but reaching out via email will work. I promise to try and reply quickly to anyone that's interested. I don't know if you can still see my slides and see the VPARs.
Thank you. I have a question, Bernardo. What is the length of time in real time it takes to process the video? And if an organization were thinking about doing week-long samples,
Yes.
7 days as part of a more comprehensive counting campaign, how soon will the technology be available for that type of application?
That is an excellent question. I think that's the main question on a lot of people's minds. We're still optimizing our processes, and so right now it still takes a significant amount of time. So that's another reason why I haven't wanted to open up the website yet. Our current the good thing is that you can parallelize a lot of the algorithms. So you can run, for example, if you do accounting that's for a week long, you can run each hour in parallel, as long as you have enough hardware. However, we're talking about response time in the measure of weeks, at least right now, for the setup that we have here at CMU. The good thing is that our sponsors here at CMU are very interested in high impact projects. So if we have people reaching out that have studies that are very impactful, then that can be we can possibly use that as a source of funding to get, for example, more hardware to be able to respond more quickly. Right now, if you do comprehensive studies for full week accounts, we're going to take at least 3-4 weeks at least to reply.
Right.
We will also try and talk and kind of prioritize depending on if this is a study that's long term and is going to have a before and after, that you're going to go back, and we'll try and kind of schedule it in a way that best optimize our resources. So if it's not high priority, we may take longer. If it's high priority, we can definitely discuss it and try and find a way to help.
Good.
I hope
That's helpful. We have a couple more questions that have come in. One is,
yes.
is your scripting available if others would want to use it? And the second question after that is, do you have any recommendations for preparing a site for monitoring? For example, trimming bushes or different types of painting on the street that might enhance the likelihood of identifying bicyclists and pedestrians. So there's two questions.
Excellent. Yeah, two excellent questions. So for the first one, we definitely, as academics, we want to publish everything, make everything available as much as we can. We're actually working on the second version of our algorithms. The first one was published in a paper. We have not made all the scripts available. They're not that easy to actually run, since on the first version they actually required specialized hardware. For the second version, that's still under development, but our intention is, once it's further along development, and once we've kind of automated it and made it so that we can be quicker on the response times, we definitely want to open it up, and at the very least publish how it works, and possibly then even share some of the code depending on how things go. And inside the university, that's not always easy to do, but at least publishing the methods, that's definitely something we want to do. For the second question, again, a very, very good question. I can tell you right away what we struggled with as computer vision researchers, at least from our group here. And one of the things is movement in the scene that's not coming from pedestrians, bikes, or cars. And that's oftentimes exactly, it's a movement of the vegetation that's just shaking in the wind, and it looks like there's something there. A lot of the algorithms depend on movement or background subtraction, so they try and kind of estimate what the background looks like and use that as comparison of what's in the background versus what's not the background. So if you have, for example, vegetation there that's shaking in the wind, that makes it always harder, because that was going to show up as, okay, it appears like it doesn't match the background. So trimming vegetation is great. I think a clear line of sight is great, is always helpful. Getting the cameras higher up and getting more of a top-down view usually helps, assuming there's enough resolution to see the bikes. So 45 degrees or higher is a good way also, that's helpful. I know that one of the commercial products that's very popular now is MyoVision. If I could ask anything of MyoVision, I've received some videos from MyoVision. If I could ask anything of that system, was to be a little bit higher resolution. So if you're going to do any new purchases of equipment to record, even if you're planning on counting it manually, I think it always helps to get a little bit higher resolution on the cameras. It would help if you have a human counting, it would help them. If you have the computer counting, it definitely helps the computer. That's for sure. And also, if I may kind of ask even more, the more rigid the setup is, so the less the camera shakes, is also helpful. A human watching a video, if it's shaking, it actually usually doesn't bother the person that's watching it that much. A computer, that's significantly more challenging. You can do things, there's algorithms to help with that, to register frame to frame, but if there's less shaking in the camera, that would be also something that would help.
And another question has come up, and that is there a frame rate that you recommend for the data reduction process to work well? Yes.
Well, actually, that's surprisingly, at least algorithms we've been working with, unless you have a setup with a huge crowd, and we really, the things we're developing are not really that suitable for crowds anyway. 30 frames per second is usually enough. We don't really need more. The pedestrians, and neither the pedestrians nor the bikes travel that fast where you can't track them at 30 frames per second. You could possibly even go a little bit lower than that, because of course we want to make sure that that all that we record is going to fit on the SD card that's there. Oftentimes the compression, so this is sometimes the traffic engineers that put the cameras up don't really have a lot of control on the compression that's being done with the video. So compression just basically oftentimes ends up being a trade-off with quality, with image quality. I believe most of these recording equipment doesn't really let you change the compression, but if possible, that's another thing that we've seen sometimes is a little bit challenging, is when the video is compressed too much to a point where the images almost become blocky. And if there's like block type images, then it becomes harder for the computer to come later on and correctly identify what's going on.
Good, thank you.
Sure, absolutely. More questions? Or
I actually have a question. How did the process work in regards to, or were there any situations where perhaps somebody on a skateboard or somebody walking a stroller or those sorts of bicycles or pedestrians that may not fit into the typical classification? How did it treat them?
So basically for the skateboard, I don't think we had any instances in this data set of these 10 hours that I was talking about, but I can already tell you that what would happen with a very, very high likelihood would be someone on a skateboard would be seen as a pedestrian, just because of the skateboard is relatively small compared to the size of the pedestrian. So likely that would be what would happen, unless they were traveling too fast, and then it would become possibly some of the low or not. The computer is not as sure as what it's seeing cases. The other strollers, for example, are a tricky object to find. Again, on this data set that we've kind of opened up and we've discussed what was seen, we didn't have any strollers. But oftentimes I've seen in other data sets that oftentimes tend to be classified as bikes. But again, it's not really clear cut. So that's one of the reasons why I would say likely most of the algorithms being developed right now are not really taking those special cases into account. And what would happen is that you either get a misclassification or you're just lucky and get a correct classification. But that's what happens. That's why you really don't have 100% accuracy, because if you think about it, even the world doesn't fit into neat categories. So getting 100% accuracy is very, very hard. On the other hand, for most data sets I've seen, that usually is not a big problem anyway. I hope I mean, that at least I feel that's the response to the fair answer to the question, even though it might not be that satisfying.
Well, no, that makes sense. I do appreciate you taking the time to answer.
Yes, absolutely.
Nathan, we have no more questions on the list. I think you want to move on now, and then we'll see what other questions. We can always come back and open it up later.
I think that sounds about right. And it's 3 o'clock, so we'll go ahead and move on to the next panelist now. We'll go ahead and get the screen switched over here to you, Tariq, and then you can take it away.
Okay. Good afternoon, everybody. I'm Tariq Sayed. Can you all see my screen?
Yes, we can.
Okay. I'm from University of British Columbia, Vancouver, Canada, and I will describe a similar system, but I will focus on applications. We have done many applications, both data collection and safety, and we've done projects in about 12 or 13 different countries, and many of these projects have been done for consulting in both Canada and the US, Europe, and Asia as well. So I'm just going to describe the motivation for this system that we developed at UBC, and we started developing this system since 2005. We had two motivations. One is automated data collection, specifically detailed microscopic behavior data collection of all road users, vehicles, pedestrians, and cyclists. But our even bigger motivation was to do safety analysis using traffic conflicts and near misses. So as you all know, road user movements and behavior are complex and difficult to capture manually, and manual data collection methods are more expensive, error-prone, and time-consuming. On the safety side, traditional road safety analysis has relied on collision data, which takes a very long time. You need to accumulate collision data for 2 to 3 years. The quality of the data is always a problem, and even collision data doesn't offer very good understanding of collision factors and how safety measures actually work. So we needed a more proactive approach, and this is where we decided in 2005 to automate the process of collecting traffic conflict data. And you will see many examples with videos in the following slides. So generally, this is how the system works. This is how we started with what we call feature-based tracking. Now we do both feature-based and background subtraction, and we combine the two clues together to get a much more accurate tracking. So you see here, features are tracked on the left, and then on the right from one frame to another. And the end, you get objects. Each object has an ID, and the number that's changing is the speed. So this pedestrian now is walking at 1 point whatever meter per second or so. This is an example of conflicts. You can see on the this is in slow motion, but this van decelerated. So on the top left, this is the deceleration, -4 meters per second square to avoid hitting the pedestrian. On the bottom left is time to collision. They were about 1.5 seconds away from hitting each other, which is a measure of the severity of traffic conflict. And you have the vehicle speeding green, and it will stop because the van will leave the scene. And you have the pedestrian speed on the bottom right, and you see this ambulation because the pedestrian is taking steps. So you see the vehicle is a straight line while the pedestrian is fluctuating, and we will use that for classification with fairly high accuracy later. It works very well, even in this is we did several intersections in Shanghai in China, and you can still track very well even in crowded scenes. This is an example of a traffic conflict. You see the cyclist, and you can see the conflict. We can calculate many things. We can calculate time to collision. We can calculate the yaw rate, which is the amount of swerving. We can calculate many other conflict indicators as well. So we can do behavior studies, and we can also do safety analysis. This is from work we've done with the New York City DOT. This is, I think, Manhattan, if I'm not mistaken. And we give them these heat maps, which shows where are the conflicts. And these are the conflicts between cyclists and vehicles. And the hot areas are where the high number of conflicts per square meter. So this is an example of a conflict for this situation, for example. And you can see the conflict between the cyclist and the vehicle. And we can collect these and draw these heat maps. We did a before and after for this location, so they did a significant improvement. And again, we can do before and after. We can do apply statistics similar to the highway safety manual, and we can get specific reductions or the effectiveness of the treatments that they apply. This is the same location, another conflict between cyclists and vehicles. You can see the cyclist wanted to go straight, and we can calculate many different conflict indicators. I think this is the third one, but anyway, it's very similar. And they did a lot of improvements at this location. I have a lot of videos and a lot of data, but for the time, I'll just show a few videos. This is Vancouver, downtown Vancouver, and you can see conflicts again. Vancouver is very active in providing infrastructure for cyclists. And again, we do a lot of before and after. Like last year, we did about 10 before and after evaluations for City of Vancouver. It's about 3 days collecting of data before, 3 days after. We do the conflicts, and we give them we give them counts, we give them average speed distributions, and many other things as well. So these are some applications that I'm going to show. I'm going to start with automated microscopic data collection, and I'm going to emphasize the word microscopic. We can do violations detection as well, and I'm going to show some examples of safety analysis. So let's start with the first one. This is tracking a pedestrian. You can see that the pedestrian has ambulations. For the cyclist, you have cadence. For the vehicle, it's mostly linear, and we can use the movement to classify the type of road user with about 85 to 90% accuracy, depending on the quality of the video, of course. So, for example, on the right, you can see 3 movement trajectories. One for pedestrian on the top, and the middle is for a cyclist. At the bottom, it is for a vehicle, and you can see the difference. We can take this signal, we can analyze the signal and get what we call the predominant frequency, and we can use this value to classify with very good accuracy. It's not very bad at all. So this is, for example, in 3 different data sets in Vancouver and Surrey, which are both in British Columbia here in Canada. And again, depending on the data set, we get 85 to 90% correct classification accuracy. The top right is a study we did in California. And again, this is a scramble phase. And you can see the pedestrians crossing diagonally. On the top left are vehicles. The bottom left is a study we did in Cairo, Egypt, and you can see pedestrians moving everywhere. On the bottom right, it is around about on UBC campus, my university, and you can see we can track generally with a very good accuracy. Collecting pedestrian data. This is from downtown Vancouver. Of course, you can have some errors like overgrouping and things like that. We try to correct them as much as we can. And we get, again, usually like an 85% accuracy is not that difficult. We can do things like that. This is speed. You can see a pedestrian will come from the bottom, and this pedestrian will stop to talk to his companion. In green, this is the green. You see the drop in the speed, and then it will go up again. So we can get a lot of very detailed microscopic behavior data that we can use for a lot of traffic applications, behavior applications, and safety applications as well. This is, for example, a study we did here. This is the worst location in Vancouver. A lot of jaywalking. It is like a low-income area in the city of Vancouver, and this is they wanted to understand jaywalking. So this is a heat map of pedestrian speeds. You see that pedestrians who are crossing on the crosswalk have lower speed than pedestrians who are jaywalking in the middle of the block, and their speed is much higher, like they are running, they are violating, and we get a lot of detailed behavior data. Again, we can get distributions and things like that. We can do things like gait analysis, and we see many applications for that. So we can take this signal, we get the predominant frequency of pedestrians, the speed profile, which most likely will correspond to the step frequency. And knowing the speed and the step frequency, we can get the step length. And we can use that in many applications, including microsimulation. We developed a microsimulation, but it's a model based on gait factors. For example, this is a study we published, again, trying to classify gender. Again, not by looking at the shape, but just plotting step frequency, step length, and walking speed. You see that we can get about 85 to 90% accuracy. And you can see that we can differentiate between females and males. Of course, it is not accurate everywhere. It depends on the quality of the video, but it will give you a lot of good information that you can use. This is old and young, same thing. We get another 85% accuracy, which is not bad at all, again, by the step frequency, step length, and the walking speed. This is a study that we published on trying to automatically detect distracted pedestrians. And we see that their gait movements and gait stability is different. So we take things like walk speed, the step frequency, step length, walk ratio, which is the ratio between the step length and the step frequency, and some dynamic gait factors like change in gait in time, which reflect stability. And we can, just by these parameters, get about 80% correct identification of distracted pedestrians. And again, this is published work in IEEE, I think. Collecting cyclist data, this is UBC campus again. We can count. Counting accuracy is usually high. In this case, it was the video was very good. We can track with high accuracy. Of course, it will vary significantly depending on the video. This is an actual location in downtown Vancouver, and the screen line on the left is for vehicles. The screen line 1 on the right is for cyclists. And again, comparing to manual counts, for screen line 1 for the vehicles, we got about an 88% accuracy. For screen line 2, the cyclists, we got 91% accuracy, comparing to the actual manual count that we observed in the videos. We can do, as I said, a lot of behavior studies. This is UBC, the University Roundabout, and you can see the difference. This is a cyclist heat map, the speed heat maps. You see that cyclists who are moving on the sidewalk have much lower speed than the cyclists who are on the actual lanes, and the cyclists in the inside lane have higher speed than the cyclists on the outside lane. This is comparing helmet with no helmet. The cyclists who are with helmet are generally faster than the cyclists that do not have helmets, and you can explain that in many ways. More risk-taking, more experience. But anyway, it is very clear there is a significant difference between the two. What about the helmet? Here we try to get the cadence. We were able, the cadence is like from the movement and from the change in the center of gravity. We weren't very successful. You can see that the R-square is not very high, but I think it is doable, and it will depend on the quality of the video. This is another paper we published on trying City of Surrey here wanted to collect data on helmet use by cyclists. So we developed a system where we can identify a cyclist, point to the top of the object, and then use some classifiers. Depending on the shape of the head, will vary between a helmet and no helmet, and we can classify. So this is the cyclist. From the cyclist, we go to the top, and we use things like color and texture, and we ended up with 85% accuracy. But again, the tracking here was very good. We can do a lot of automated violations detection. Again, this is the same location that I described, the low-income location in Vancouver. And the city wanted to identify jaywalking. And also, so they wanted to identify spatial violations and also temporal violation. And we were able to identify both with very high accuracy. This is from China, Shanghai. You can see a violation, both spatial and temporal. This person should not be crossing at this time, and he's crossing outside of the crosswalk. He's a very cool pedestrian. You see that he will be involved in many conflicts, but he will not change his movement whatsoever. Interesting. So, this is a study we've done with in New York. Again, you see that's downtown New York, Manhattan. You can see spatial and temporal violations as well. And these are very useful because they have safety implications. Let me show you some safety analysis. This is trying to see how pedestrians behave in conflicts. You can see these three graphs, the speed of the pedestrian on top, the change in step frequency on the middle, and the change in step length at the bottom. And you can see that the pedestrian will run, and you can see the increase in the speed and also the step frequency. And this is another way of trying to identify what we call evasive actions. In conflict situations, you can see the pedestrian will stop, and you can see the drop in both the step frequency and the speed will become to 0. And we can use that in combination with things like jerk, deceleration by vehicles to identify the severity of a near miss or a conflict situation. One very useful application is to do what we call before and after safety studies, and we do many of these. The problem with relying on collision data to do before and after safety studies is that it takes a long time. Collisions are rare events, and the quality of collision data is a problem. So you need to apply these very sophisticated statistical techniques, and you usually end up with a strange situation where the safety analyst, for the sake of methodological correctness, will strive to observe events that he needs to prevent in the first place. So he wants to observe more collisions to get a statistically valid outcome. These are examples from the evaluating a scramble phase in California. On top, the intersection before, at the bottom, the intersection after. And you can analyze, you can see the vehicles on the left and the pedestrians on the right. You can see the diagonal crossing at the bottom right, which is scramble phase. And you can see examples of conflicts. This is in slow motion. And this pedestrian, for example, entered the intersection late. We can identify all of these automatically. And we can do things like that. These are heat maps. And you can see where the conflicts, the right turning vehicles and the pedestrians crossing, and you can see the before and after. And then we can give the road authority something like this. These are the distributions of the conflicts. In this case, the conflicts is represented by the time to collision, how close they were to collide. We also have deceleration and something called post-encroachment time. And you can see in all of these indicators, there was significant drop. The blue line, the blue distribution is before, the red distribution is after, and we can convert these to actual reductions using some statistical techniques. And when we compare these reductions to what we get using collisions, they are very similar. We published 2 papers comparing before and after safety results using collisions and using conflicts, and there was significant similarity between the overall results. This is another example of a before and after safety evaluation that was done in downtown Vancouver here. You can see on the left the intersection before, you can see on the right the intersection after, and they wanted to know quickly whether this treatment was effective or not. I'm just going to show you some examples of conflicts in the before period. And again, we have these heat maps, and we produce overall improvement or effectiveness of the treatment. As I said, we're doing a lot of projects worldwide, and we are very interested in working with more clients at the university. Thank you.
Great, thank you so much, Tariq. Now we'll move on to any questions that we have for you.
Eric, we have a few questions. What's the level of human interaction required to tweak the algorithms to optimize the classification and the segmentation?
It depends significantly on the video quality. As the first speaker said, if I have a camera that's high enough, we can usually get very high accuracy of tracking. The problem that in many cases, cities send us videos from the signal head level, and we can work with these, but in some cases, we may intervene manually. So you can use the system at least as a filter to give you all the important events. And you can look and identify some events that may be like identified by error. But overall, we have very good accuracy ranging between 80 and 90%. Unless you have a very poor quality video.
Okay, good. We have one comment that is just amazing work, well done. And a second question is, how is performance impacted by time of day or lighting? And you face constraints in that realm?
That's an excellent question. As I said, we do many of these for different cities. We have about 5 major clients in Canada, 5 major cities, and we do a lot of these. We analyze their what they call accident-prone locations, and usually what we decided to do is to take 2 days of video recording before and 2 days of video recording after, and these usually go from 7 a.m. to 7 p.m. We don't go for night conditions. Sometimes the night conditions, you can get very good tracking, especially if you have, because you can track the headlights of vehicles. But again, from what we've done over the last 10 years, we usually go 7 to 7, so we do not cover night conditions.
Okay, and a couple questions here. How long does it take to process an hour of video? And have you done any applications where the goal was to characterize an entire city or network to identify hot spots? So at the planning level, for example, jurisdictions could decide where to focus efforts.
That's an excellent question. Again, it depends on the complexity. Like the Shanghai one, for example, was challenging. But I would say for each hour, maybe like 5 hours or 7 hours, something like that, of processing. We haven't. We like what usually when we work with different cities, what they do, they use collision data and also like talking to the public to identify their top prone locations. For example, City of Vancouver each year will give us about 10-15 locations that they think are problematic, and we do detailed analysis for these, and we write reports. I can, if anybody's interested, I can give a copy of a report, a recent report, for example, that we did for City of Calgary or City of Edmonton in Alberta, Canada. And we tell them what is wrong, and we also can recommend, like a safety audit, you can recommend improvements based on the conflicts. We do before and after, and usually these are very effective. But it happened on several occasions that we analyzed locations and we see nothing wrong. So you can get like public are worried about a location, and this is usually very good, and you can make comparisons. So the more locations we do, we can establish benchmarks for different conflict indicators, conflict severity, conflict rate, and so all of that, and we can compare. And we establish distributions, and we say this location is not in the top, whatever, 20%. But we haven't yet done a citywide where we take 500 signals and do all of them and identify the top based on the video.
Okay. Here's a question for both panelists. It asks you to see into the future. Do you see that video, like you're both working out, will remain the dominant news and become the dominant news source of data collection? And what are the pros and cons comparing it with infrared and LiDAR and other technologies that people are beginning to experiment with?
Who would you like to start?
It's both of you could answer that one. They ask for either person.
I think computer vision algorithms are becoming much more accurate with time, like compared to how we started 10 years ago. And now we can combine different techniques of tracking. The results are as good as the quality of the trajectories you get from the analysis. However, the same methods can be applied to any trajectory. So for example, in the future, everybody will be connected, and you can get the same trajectories from connected vehicles, connected pedestrians, and all of that. So these will work on the trajectory level. And so these techniques are independent of the method of collection. However, computer vision using video data is becoming more mature with time. But of course, there are problems like occlusion, for example. If you cannot see it, or if it is occluded, then you cannot track
it. And this is Bernardo speaking. Just to add, I do definitely agree with Tarek. A lot of the methods that Tarek's shown here actually go past the computer vision and can be applied to anything. Usually what I've been doing more recently is more based on computer vision. And it's true, it's been maturing a lot. I think the other factor is also that the cost is getting lower and lower. And cameras are becoming more and more ubiquitous. So I definitely see computer vision being the main source of traffic studies for a number of years. But again, once we get our societies become more and more connected, it may actually become less and less relevant. If every single pedestrian is connected to the infrastructure, then there's not even any need for computer vision. So that's just really what I have to add.
Another question has come up. How do you store data for long-term SQL, or do you store the video itself? What are the mechanics of keeping track of all the vast volumes of data you're collecting?
That's an excellent question as well. I mean, storage is becoming cheaper, but for us, for example, every time we do a project, we receive the data from the city. Usually, we don't collect the data ourselves. And once we finish the project, there is a hard disk somewhere in my office with the project title and number. We don't have like a supercomputer with huge storage yet, but I think these are becoming cheaper. I'm not a computer scientist, but storage is not an issue now. We have cheap storage that we can use.
And actually, to add a little bit of a spin to that, now for our US-based attendees, the federal government is actually putting more, if it's funding the project, it's actually putting more restrictions or demands basically on the information being released. So, for example, I can already tell you that the latest funding sources that we've gotten have actually demanded that we make the data that we collect public. So if the city collects it, then we don't have to make it public. But if we ourselves collect it, then we have to make it public, and that's actually been a significant, I don't want to say headache, but it's a significant hurdle when you're looking for funding for these things. Actually, there's a couple of services popping up. Some of them are even free that let you upload the data. But with video, that's always trickier because video can be significant, can be a significant resource. So, for example, a full week of video is quite a lot of data.
Thank you.
Sure.
Nathan, I see no other questions in queue at this point.
Okay, which is actually a great timing because we only have a few more minutes left. So we will go ahead and wrap up here. Mai, if you can go ahead and switch to back to your screen, we'll go ahead and finish this out. And Bernardo and Tariq, thank you both so much today for coming and presenting and talking about your research and your projects. I believe this was incredibly helpful, not only just for ourselves, but all the attendees here to learn more about how video or various different methods and ways to collect bicycle and pedestrian data, the ways that you can use this data for different analyses. The next session that we will be having as part of these conversations with colleagues is tentatively scheduled for Tuesday, June 26th. And that topic will be in regards to big data and bicycles and pedestrians. And we'll have more information on that in the coming weeks as we finalize that session. Again, thank you everybody for taking part in today's webinar. We really do appreciate you taking the time. Again, Bernardo, Tariq, thank you both so much. We appreciate your time, and we hope everybody here has a good day. And Greg and Mai, both of you, thank you as well for managing things behind the scenes.
Thank you.
All right, with that, we will go ahead and end today's webinar. Thank you.
Thanks.